As you start to work on these polynomial functions, you're going to feel like you're being asked to complete a lot of steps. So look at this, g of x equals x to the fourth minus 8x squared. You're asked for the domain, the x-intercepts, the y-intercepts, the increasing, decreasing intervals, the local max, local min, concavity, inflection points, and the graph. Some of this we can shortcut with calculus, and I want to show you how that works. It's only the calculus part, though, that we can shortcut. So let's start with the domain. Domain, this is a polynomial, it's negative infinity to infinity. The x-intercepts, that says, well, where is this equal to 0? X to the fourth minus 8x squared equals 0. You can factor out an x squared, which leaves you with x squared minus 8. When you set that equal to 0, you get x squared equals 0. So x is 0. You get x squared minus 8 is 0, which says x squared equals 8. That'll give you x is plus or minus the square root of 8, so 3 x-intercepts. Y-intercept, there will be 1. It's when I put in 0, which in this case is 0 to the fourth minus 8 times 0 squared. That's just 0. And we kind of knew that already when we got x equals 0. We know we're also going to get y equals 0. I'll just write that as a 0.00. Okay, so we have our intercepts. This is where we're going to shortcut it, where we're looking for the increasing, decreasing, local min or max, the concavity, and the inflection points before we graph. So I rewrote the function down here, and we're going to start by taking the first derivative. So I have x to the fourth becomes 4x cubed minus 8x squared is 16x. I want to set this equal to 0. I notice they're both multiples of 4. They both have an x, so I'm going to take out 4x. Times x squared minus 4 is 0. This says 4x is 0, x squared equals 4, x equals 0, x is plus or minus 2. So I have 3 numbers that are my critical points. Now eventually, I'm not going to do it right now, I'm going to have to plug it back in to get the y value, so I really have a point instead of just a number, but right now I'm okay with just the number. So let's just put Cn right here to say critical number and move to the next step. Next step is take the second derivative. So 4x cubed becomes 12x squared, 16x becomes 16. I'm going to set this equal to 0. I say 12x squared minus 16 is 0. Says 12x squared equals 16. X squared is 16 over 12, and I take the square root. Like before, I'm going to have plus or minus. Let's look in the square root. 16 over 12, I can reduce that to 4 over 3. I'm okay with it just like that. I don't need to put that in the calculator, get a number, rationalize the denominator. We're just going to keep these. Now these are our potential inflection points. And again, we don't have something called inflection number. We only have the x, but that's okay. What am I going to do from here? I'm going to look at the concavity. So we're going to take the real number line because that was our domain. I have negative square root of 4 over 3. I have positive square root of 4 over 3. I need to pick a number in each interval. Let's say we pick negative 2, 0, positive 2. If this worries you, like you're worried about what the number the square root of 4 over 3 is, put it in your calculator. What I was thinking is 4 over 3, a little bit bigger than 1. When I take the square root, it's still going to be about 1, so picking 2 was a safe bet. If you're worried about it though, use your calculator, that'll help you out. Okay. What are we going to do with these numbers? We're going to put it into the second derivative, which was 12x squared minus 16. So think about negative 2 squared is 4, 4 times 12 is 24, 24 minus 16 is positive. Positive means concave up. 0. 12 times 0 squared is still 0. 0 minus 16 is negative. That says concave down. And then 2. 2 squared is 4. 4 times 12 is 24. 24 minus 16 is positive. That's concave up. Right. So notice we haven't done increasing, decreasing. All we've done so far is concavity. But now we know the concavity. We know the inflection points. But that really tells us a lot more. Look at concave up, concave down, concave up. Concave up says if there is a critical number, that one will be the local min. Concave down says we have a local max. And then concave up again says local min. Now, not really on purpose, but it does happen to be that the -2, 0, and 2, when I scroll back up, were my critical numbers. Now, I didn't really plan that on purpose, and I should say that I did to make me sound smarter, but that's not what just happened. But you do see those 0, positive, and -2 were my critical numbers. So what does that say? It says I know where my max and my min happen. I also know that increasing, decreasing changes at the critical numbers. So remember, this is -2, this is 0, this was 2. Now look what was happening. The graph was going down. So from -infinity to -2, I had a decreasing interval. Then it hits -2, and I can see it's increasing. And it doesn't stop increasing until it hits 0. So -2 to 0, increasing. Then I get to 0, and I decrease. So where do I stop decreasing? When I get to 2. And then the last interval is 2 to infinity, and it's increasing. So without doing the first derivative test, I still have the increasing, decreasing intervals by looking at the concavity. So now we're ready to graph this, which means we are going to have the y values for our critical numbers and our inflection points. So let's write them down. We need to know -2, 2, 0, the square root of 4 over 3, and negative the square root of 4 over 3. To get these, I'm going to use Desmos. I'm going to put the original in and just do a table to get these values. So we'll start with f of x is equal to x to the 4th minus 8x squared. And then I'm going to hit the settings, say make a table, and we're going to put in the values that we wanted to know. So we want to know 0, 2, -2. So I have the square root. I'm going to put a parenthesis 4 divided by 3 to make sure it takes the square root of both of those. And then I can do the same thing for negative the square root, and I'm going to do parenthesis 4 divided by 3. So now we know -2 is -16, +2 is also -16, 0 we know is 0, and square root of 4 over 3 and negative square root of 4 over 3 is about -8.9. Looking at my numbers, I see -16, -8.9, and I know this graph needs to have more under the y-axis than above it. I'm going to do these in twos, so 2, 4, 6, let's call that -8, 2, 4, 6, let's call this -16. Okay, so +2, -16, -2, -16, 0, 0. Square root of 4 over 3, a little bit bigger than 1, and then down under the -8. Same thing on the other side, we can see this symmetry. So I kind of want to highlight these two numbers, the square root of 4 over 3 and negative the square root of 4 over 3. These are inflection points, so I want us to think about what happens at inflection points. In inflection points, we change concavity. The beginning concavity I can see, if I'm going from square root of 4 over 3 to negative square root of 4 over 3, I can tell this was concave down. Now it's going to change concavity, which says it's going to be concave up. Same thing on this side, it's going to be concave up. We happen to know as it's concave up, if we go back, we're looking for our x-intercepts. And we know they're at plus or minus the square root of 8. Square root of 8 is going to be a little bit less than 3 because the square root of 9 would be 3. So we know just close to that, but not exactly at 3. We can put some points. So let's say if we call this 3, we call this 3. Somewhere in here it's going to be the square root of 8. So as it's coming up, it's going this way. As it's coming up, it's going this way. Now check out what we said. We said it would decrease until it got to -2, and it did. And then we said it would increase from -2 until 0. Then it would decrease from 0 to 2 and increase from 2 to infinity. So our graph matches what we said would happen. You have all the information that you need. Let's write on here local min, and then the 0, 0 is my local max. So don't feel like you have to do things in the order that it's presented. You can go back and answer the questions after you've used the second derivative test to find out all the information.